In the last class, when I was discussing the isoelectric point of amino acids, so the different ionic forms for histidine was not observed in that video. So I am taking the case of histidine here again. So as you can see, the ionization constant of this alpha carboxyl group is 1.82, and the ionization constant for the alpha ammonium group, that is this one, this is 9.17, and the ionization constant for the side chain amine group is 6. Now moving to the pH values, first of all we have dissolved the solution or dissolved that amino acid, that is histidine, in such a solution having a pH less than 1.82. This is the ionization constant of alpha carboxyl group. That means we are giving highly acidic conditions. So under such acidic conditions, we can see all the groups, that is alpha carboxyl group, and this is the ammonium group, as well as the side chain group is protonated here. Now this group is protonated, this is protonated over here. Now you can see here this 5-membered 2 nitrogen containing rings, 5-membered ring containing 2 nitrogens. Now which nitrogen will get protonated? Okay. Now this is a pyridine type nitrogen and this is the pyrrole type nitrogen. If you can see the aromatic behavior of pyrrole and pyridine, so it can be easily explained from there that this non-pair of electron over this nitrogen is readily available for the protonation. However, this non-pair of electron, which is over here, is undergoing delocalization for the aromaticity of this 5-membered ring. So this nitrogen is readily available, the natural electron pair is readily available for protonation. So we can say that, in other words, we can say that this nitrogen is more basic than this nitrogen. So that's why the protonation is occurring over here, not at the nitrogen. Okay, this is clear. So that's why the protonation is here. So this is a dicationic form because overall there are 2 positive charges. Then we have make the pH of the solution now greater than this 1.82, which is the ionization constant of this alpha carboxyl group, but less than 6, which is the next pH we have, because we have 3 isoelectric points, sorry, 3 ionization constants, that is 9.17, 6 and 1.82, and we are moving gradually to the upper ends. Okay. So when the pH of the solution is greater than 1.82 but less than 6, then what will happen? Now under such conditions, the pH becomes greater to the alpha carboxyl group. So now this group is going to be ionized. So this group is ionized. You can see this alpha carboxyl group is ionized. Now from acidic to it is converted to the basic group. And here this ammonium ion and this side chain nitrogen is remaining protonated. In the second case, in the third case, when the pH of the solution is greater than 6, but less than 9.17, which is the next pK. So under such condition means the pH is between 6 and 9.17, because greater than 6 but less than 9.17 means the pH is in between, somewhere in between 6 and 9.17. Under such conditions, what will happen? Now the pH is greater than 6 means the side chain, this is the ionization constant, 6 is the ionization constant for the side chain. So this nitrogen is ionized. Now it will deprotonate, and this is ionized over here, and this NSC positive remains again protonated. Okay, now you can see here this molecule contains 1 positive and 1 negative charge, means deuterion. It is a deuterion because it had 2 charges, and total electrical neutrality is there one positive, one negative. So the molecule is, as a whole, the molecule is electrically neutral. So such a form is called deuteronic form, where, and the pH where this deuteronic form exists, we know that the pH is known as isoelectric point. Okay. Now moving on the third case, when the pH, the solution becomes 9.17, this is the highest pH for this case. Under such conditions, now the pH of the solution is greater than 9.17. So this could be also going to be ionized. Now this can be ionized, but this is a fully differentiated form. All the groups are ionized here under highly basic conditions. So this is the anionic form of this hydrogen molecule. You can see it's a one negative charge. So you can summarize from here. This deuteronic form is in between pH 6 and 9.17. It means how we will calculate the pH of the solution, pH of this hydrogen molecule? Simply by adding these two pH values, that is 6 and 9.7, and taking their average, and this will be the pH of this hydrogen molecule. Now, one thing I want to tell you here, that is, see here, see the molecule and see. When pH is greater than pi of that particular amino acid, I am talking about a particular amino acid as a generalized case. Okay? So in general, when the pH of the solution will become greater than the pi of that particular amino acid, then anionic form of that particular amino acid will exist. And in the case when pH is less than pi of that amino acid, then the cationic form of that amino acid will exist into the medium, into the solution. Now see, apply that condition here. Here, we can see the pi of this hydrogen molecule is 7.56. So when the pH of the medium is less than 7.56, we can see here and here both the forms are cationic forms. So when pH is greater than this, pi, anionic form will exist. So when the pH, now you can see the pi is 7.57. So the pi is greater than pH, means when the pH is less than pi. When the pH is less than pi, that is the cationic form will exist. Now you can see here the pH is in between 1.8 to 1.6, means here the pH is less than 7.56. Again here the pH is 7.56, because here the pH is less, again 1.82 here. So here the pH of the solution is less than 7.56, and here again the pH of the solution is less than 7.56, that is the pi of this hydrogen molecule. And what is the condition? When pH is less than pi, then cationic form exists. So here the pH is less than pi is 9.17, so 7.56, so pi is 7.56 for hydrogen molecule. So here you can see the pH is less than 7.56, and here also the pH is less than 7.56. So in both the cases, the cationic form exists. This is dicationic form, this is cationic form, monocationic form. And when the pH is greater than pi, that is the isoelectric point of that amino acid, that is here in case of histidine it is 7.56. So here we can see we can see the anionic form is existing, because here the pH of the solution is greater than 9.17. So, and the pi is 7.56. So here the pH is greater than pi, so anionic form is existing. So this is the generalized case for all the amino acids. For all the amino acids, this will happen. Okay, and this property of amino acids we are going to use here. That is separation of amino acids. Okay. See, separation of amino acids. Now you have hydrolyzed a protein or peptide molecule. Okay. And after hydrolysis, you will get a mixture of amino acids. Or suppose you have a mixture of amino acids and you want to separate them. And you separate them and we want to identify them. What are these amino acids? Okay. So under such condition, how will we separate these amino acids? For separation of amino acid, we use a technique, and that technique is called electrophoresis. Now, what is electrophoresis? Electrophoresis is migration of ions under electric field. That is electrophoresis. Simple definition of electrophoresis is, that is, if ions migrate in any electric field, that is electrophoresis. Okay, so that technique of electrophoresis we will use for the separation of amino acids. Okay, suppose I am taking an example. Suppose I have a mixture of 3 amino acids, and I want to identify them. I want to separate out them. I want to know that what is the mixture, what are the amino acids in this mixture. So what I will do, what we will do, we will dissolve these amino acids in water or any solvent in which these amino acids can dissolve. Both 3 amino acids can dissolve. So we will dissolve these amino acid mixture, small amount of this amino acid mixture. Okay, and spot them in a filter paper, in a piece of filter paper, and we will make a spot of these amino acids in a filter paper in the middle of the filter paper. So what I have spotted them over here. This is a piece of filter paper or a gel. It may be a TLC, it may be a TLC. Okay, so I have spotted over here at the middle of the piece of filter paper or onto a gel. Then put this paper or this gel into a buffered solution. Buffered solution means such a solution whose pH is fixed, is not going to be changed with the time. Okay, so we have to immerse, we have to dip, we have to immerse this piece of filter paper having a spot of mixture of amino acids dipped into a buffered solution. Suppose I have taken a buffer here, pH of buffered solution, that is medium, that is 6. So buffered solution means a solution is having a fixed pH. So I have taken as an example. Suppose I have dipped this solution, reaction mixture solution, mixture of amino acids, which is spotted on a piece of filter paper on a TLC in a buffer solution having pH 6. Okay, and then apply and then this solution is, and then electric field is applied over there. Then what I have to do? I have to do an electric field has to be applied over there. It means there is a positive electrode, this is negative electrode. Just what is the experimental setup? Experimental setup is that we have a solution, a buffer solution, that is pH 6. Okay, and a mixture of amino acids spotted on a TLC or a piece of filter paper, which is immersed into this solution, buffer solution, and also applied we have also applied a electric field over here, that is this is anode and this is cathode. Now when the electric field is applied, when these are 2 electrodes, now apply the electric field or into the circuit. So what will happen? This is the positive electrode and this is the negative electrode. Now I have, for the example, I have taken these amino acids. The examples like lysine I have taken, and I have taken here alanine, and this is the aspartic acid. And we know the anionic form, that is the PI for aspartic acid is 2.98, and the PI for this alanine is 6.02, and PI for this lysine is 9.87. Okay, and what is the pH of the buffer solution? What is the pH of the medium in which the electric field is going to be applied? That is 6. Okay, now see this condition. When pH is greater than PI, anionic form will exist. Okay, so PI of lysine is 9.87, and pH of the medium is 6. Here we can see pH is less than pi. pH of the buffer solution is less than pi of the amino acid, then cationic form exists. So we can see this is the cationic form. This lysine molecule, 2 positive charge, 1 negative charge, overall 1 positive charge. So cationic form of this lysine will exist here. Okay. And what about this alanine? You can see alanine has a pi of 6.02 and this is immersed into a medium buffer solution of 6. So it will obviously and exist in this cationic as well as in ionic form, because pH is equal to pi, and when pH becomes pi, that is deuteronic form. This is the condition for deuteronic form. When pH is equal to pi, when the pH of the buffer solution, pH of the medium will becomes equal to the pi, then obviously the deuteronic form will exist. So this is the deuteronic form for this molecule. Okay, means to the total electrically neutral molecule. Now see here the pi of aspartic acid is 2.98. Okay, now the pi of aspartic acid is 2.98 and the pH of this buffer solution or pH of the medium is, in which this TLC is dipped or this filter paper is dipped, is 6. So we can say pH is greater than pi, and when pH is greater than pi, anionic form will exist for that amino acid. So this is the anionic form of this aspartic acid, 2 negative charge, 1 positive charge, overall anionic form. Okay. Now you have applied the current. Once you have applied the current, what will happen? The ions are charged. So the charged ions will migrate towards the opposite electrodes. This lysine has positive charge. It is migrating towards the negative electrode, that is cathode. And this anionic form, this aspartic acid, has negative charge, overall negative charge. That's why it is migrating towards this anode, that is positive electrode. And this pi, so the alanine molecule is not going to be migrated anywhere. Why it is not migrating? Because it is electrically neutral molecule. So what we can see, there is 3, and but initially we have applied a mixture over here. Now these amino acids are separated. Okay, these amino acids are separated here, but still we can't see them because they are not colored. There is no color at all. So we have to now, if we want to see them, where is the spots are there, where is the amino acid position of amino acid, then what we will do? We will apply a solution of, we will spray a solution of, we will dry this TLC or this filter paper, and then we will apply a solution of ninhydrin. This is the ninhydrin solution. This is this experiment you have also done in first or second semester. Okay, when you were performing the circular paper chromatography of amino acids, then again there the visualizing agent is this ninhydrin molecule. So what is happening here? This ninhydrin molecule is reacts with this amino acid and form this complex. This is purple color complex. The color of this complex is purple. So when this ninhydrin molecule reacts with this amino acid, this purple color complex is going to be formed. So what we have done? We have sprayed ninhydrin solution here and kept it in the oven for around 60 to 70 degrees centigrade. Then this purple color spot is originating there, appearing there. Why this purple color solution color spots are there? Because this is the amino acid and reacting with this ninhydrin to form this complex. And now suppose you have, see, here one ion is positive, one ion is negative, and this is electrically neutral. Suppose in a mixture we have 2, 3, 4, 5 amino acids are amino acids there, and see if there are 2 or 3 or more than 3, more than 4, more than 5 similarly charged ions are there, similarly charged amino acids are there, then under such condition the amino acid which is heavier obviously will migrate slowly, and the amino acid which is lighter, having a low molecular weight amino acid will move faster in this under the electric field. So they will again separate it out. Okay. So by using this condition, so this force are appear over here, and matching these migration values in the literature already reported literature values under electric field in a particular electric field, we can compare them and we can identify these amino acids from this electrophoresis technique. So this is all about this separation of amino acid and using electrophoresis technique. Okay. Now, next topic is synthesis of alpha amino acids. Now we have done a general introduction about the amino acids, their properties, okay, their acidic and basic properties, and their electrical properties, that is ationic form, anionic form, and deuterionic form. Okay. Now we are moving to the next part, that is synthesis of alpha amino acids. Okay. How will we synthesize these amino acids in our own laboratory? However, these are naturally occurring amino acids. Amino acids are naturally occurring molecules. They occur in the nature, but how we can synthesize these molecules into our own laboratory? So the first method for synthesizing these amino acids, or we can say the first starting material for the synthesis of these amino acids is alpha halo acids, by using alpha halo acids. So alpha halo acids, this is the starting material for synthesizing these alpha amino acids. So from alpha halo acids, for synthesizing the amino acids from alpha halos, we have a number of ways. Okay, so I will talk these different techniques using these alpha halo acids one by one. So I am taking the first case using alpha halo acids. This is the reaction. Okay, in this reaction, I have started the reaction from carboxylic acids, because we know that the alpha halo acids are obtained by the alpha halogenation of carboxylic acids by a reaction called Hell-Wohlhard-Zielinski reaction, that is HVZ reaction. Okay, whenever we need alpha halo acids, and the alpha halo acids can be prepared by using carboxylic acids. Okay, so starting from carboxylic acids, I have taken carboxylic acid here. This carboxylic acid is treated with PBr3 or PX3, halogen halide, or simply phosphorus halide or phosphorus, or simply we can take a phosphorus halide or phosphorus here. Okay, I have taken PBr3 and bromine, PBr3 and bromine, and I am getting this alpha halo acid. This bromine is here at the alpha position, and this is the alpha halo acid, this is alpha bromo carboxylic acid there. Okay, when this alpha bromo carboxylic acid is treated with ammonia, what will happen? It will simply undergo a nucleophilic substitution reaction at this position. So this nucleophile will come here, and bromine will go out. So by the removal of SBr, we have this alpha amino acid. So by a very simple way, I can prepare this alpha amino acid by using this technique, by treatment of this alpha halo acid with ammonia. Okay, through a nucleophilic substitution reaction. Now, what is this Hell-Wohlhard-Zielinski reaction? Hell-Wohlhard, as I already told you that, what is Hell-Wohlhard-Zielinski reaction? That is the alpha halogenation of carboxylic acids. It's called Hell-Wohlhard-Zielinski reaction. And simply, most of the cases, the alpha halo is alpha bromo acid, alpha bromine. Okay, so this Hell-Wohlhard-Zielinski reaction is generally used to prepare alpha bromo acids or alpha halo acids. Okay, now what is the course of the reaction of this HVZ reaction? This is the alpha carboxylic, this is the carboxylic acid having an alpha halogen. Okay, your alpha halogen must be there. If there is no alpha halogen, then there is no sp3 reaction. So such carboxylic acids having alpha hydrogen, they will give sp3 reaction. Okay. This is treated with PBr3. Here, this C double bond O is polarizing here, ionizing here, and this P for phosphorus is act here, releasing this Br minus ion. And further, now this will react here, and further, this OPBr2 is here. This Br minus is coming here, and this is OPBr2 going out. Okay. Now, after this, we have this molecule. What is this molecule? This is actually alpha bromo carboxylic acid. Sorry, this is alpha halo. This is actually acid bromide. This is acid bromide. This is simply RCOX. This is acid bromide. So this acid bromide, it undergoes enolization. This is also known as tautomerization, or simply we can say 1,3 sigma tropic shift of hydrogen. Okay, so this is enolization or tautomerization, and this is simply 1,3 sigma tropic shift of hydrogen. Now see, this form, we know that this keto form is more stable than this enol form. You also know that there are some cases where enolic form is somewhat stable, and this stabilization is due to hydrogen bonding, or some other cases like that case of ethyl acetate. So, but here this keto form is more stable than this enol form. But for the reaction, this tautomerization is going there. Now this hydrogen is coming here like that. This is the mole movements. This hydrogen is coming to the oxygen and converting to the enol form. Now, what was the reagent? Reagent was PBr, Br, bromine. Now the bromine is actually coming here. As an electrophile, bromine is coming as an electrophile here. This Br plus is coming here. So this is this Br2 plus, sorry, Br bromine. Br2 is acting as an electrophile here. So it is actually electrophilic substitution. Hydrogen is removed, and this electrophile is coming here. The course of action. Okay, so this Br plus is coming here from the bromine, and this S plus from which have been extracted from here to here, now removed into the system. Means this Br plus, actually this Br plus is replacing this S plus from here. This is an electrophilic substitution at alpha position. Here the electrophile is Br plus, and leaving group is H plus and is the proton. Now we have this alpha bromo acid bromide. This alpha bromo acid bromide will react with another molecule of carboxylic acid. And what will happen? Now this Br plus is transferred from here to here. This Br plus is transferred from this alpha bromo acid bromide to this carboxylic acid molecule, forming this alpha bromo acid or alpha halo acid. Leaving it, now what will remain here? RCH2. This is the H here. So now what will be here? It is RCH2. This that H from here to here is actually simply interconversion. Bromine is going here and hydrogen coming here. This will RCH2COBr, RCH2COBr, and no, here you can see this is the RCH2COBr. This is acid bromide. Again, will go into the reaction, and this cycle will remain again and again until the starting material consumed, that is until the carboxylic acid is available. Once the carboxylic acid is completely consumed, the reaction will be completed. Okay. Now, what I want to tell you here that this halogen atom into the alpha position of this alpha halo acid, which is the starting material for this preparation of this alpha amino acid, is actually coming from this Br2, not from the PBr3. So this halogen atom from PX3 is not transferred to the alpha position, mind it. And this statement is verified by these two reactions. Okay? Here we have, what is this molecule? PHCH2COOH, which is a carboxylic acid having alpha carbon atom. This is called phenyl acetic acid actually. This phenyl acetic acid is reacted with Br2 and PCl3, not PBr3. Now here, in the alpha position we have bromine, not the chlorine. It means this, at the alpha position, halogen is coming from Br2, not from the PX3 or PBr3 or whatever the case. And this is the report from, this reaction from organic synthesis CV6403. This is the report from there. This reaction is cited from there. Okay. Now, is another reaction, the cyclobutane ring and having a carboxylic group attached with cyclobutane ring. It's treated with bromine in red phosphorus and the solvent is methanol. Now here, no PX3, PCl3, PBr3, only phosphorus is there. And under again such conditions, the bromination is occurring at this alpha position. So this also suggests that the bromine is coming from Br2, not from PX3 or PCl3 or PBr3. Okay? And this example is from the tetrahedral letter. And this report is published there in 1996 and volume 37, page number 6. We were talking the synthesis of alpha amino acids, and first method I have discussed, that is from alpha halo acids or from carboxylic acids, because these alpha halo acids are derived from carboxylic acids. So first method from alpha halo acid, in the starting material is alpha halo acid or carboxylic acids or carboxylic acids having alpha carbon atoms. Okay. Now the first method from alpha halo acid, which we have discussed, that is direct elimination of alpha halo acids. When you take alpha bromo carboxylic acids and this is treated with amine, so directly it can form alpha amino acid. But this procedure is this procedure gives very small yield of the products, or the product yield found by this method is not satisfactory. This reaction, direct elimination reaction, gives very small amount of the product, very less yield. So this method is further modified by Gabriel. This is known as Gabriel procedure. It gives better yield compared to the direct elimination reaction, that is the reaction which we have discussed. This is the first reaction, okay, which we have discussed. Now see, one thing I want to tell you, that before planning the synthesis of amino acid, you must know the structure of the amino acid, or you must memorize the structure of the amino acid. If you don't know the structure of the amino acid, so how will you synthesize that particular amino acid? So going for the synthesis of a particular amino acid, if somebody asks you to synthesize methionine, now if you don't know the structure of the methionine, then how will you synthesize the methionine? And one more thing, that you know that this moiety, that is this moiety for the alpha amino acid, for all the alpha amino acid will remain same. This moiety for all the alpha amino acids will remain same, that is NH2CH and COH group. So all the alpha amino acids will differ only at the side chain. So by applying any procedure, you must this introduction of the NH2 group and COH group and this CH will remain same for all the synthesis of all the amino acids. But only difference is that, only variation is that the introduction of the side chain. How will you introduce the side chain? Okay. So now under this Gabriel procedure, I am taking the example of methionine. Okay. Now this is the structure of methionine. You can see methionine over here. See, this is the structure of methionine, having CH2, CH2, S and E a side chain. Because this moiety will remain same in all these amino acids. Either I will synthesize methionine, I will synthesize glutamic acid or some other amino acids. So this chain will remain, so this moiety will remain same for all the amino acids. The only variation is this side chain. So we have to think, we have to concentrate on that side chain. So now I have to synthesize this molecule, this is methionine molecule and this is the chain. Okay. Now I am starting this synthesis from this alpha haloester. What is this alpha haloester? Actually this alpha haloester is obtained from a carboxylic acid. This is a dicarboxylic acid, you know that is malonic acid. COH, CH2COH is malonic acid. If we go for this alpha halogenation of this malonic acid through HVZ reaction, we can get this alpha bromo acid, and this acid is converted into the ester. Okay. This alpha haloester, this is a malonic diethyl malonate, alpha bromo diethyl malonate, is treated with this potassium thalamide. And what is this? This is the amide of phthalic acid. And this amide of phthalic acid is converted into sodium salt. This is a potassium salt of amide of phthalic acid. This is called potassium thalamide. Okay. Treated with this one, so what will happen? This KBr will be from here and this and here. Simple reaction. Okay. So like that, and this end is from over here. Nucleophile right there. Because you know that for the malonic acid, this is a whole in your second year, that is malonic ester synthesis. Because we know that the malonic ester is a very good starting material to synthesize a number of molecules. And that this whole reaction sequence is called malonic ester synthesis. Okay. So by virtue of this malonic ester synthesis, we are utilizing that virtue. Actually, this is an actimethylene group. So this nucleophile is in here, and we have this molecule. Now see, there is one more hydrogen which is activated. Because this is a malonic ester, this is the diethyl malonate, COET and COOET. You see, it has two active hydrogen. It's called actimethylene group. If a methylene group is attached with electron withdrawing groups, now this hydrogen gets activated. That's why this is called actimethylene group. So this diethyl malonate has two active hydrogens. One is already replaced from here by bromine, and another one is replaced by the base. This is acidic in nature. These hydrogens are acidic in nature because these are activated. This center is highly electron deficient center because here is a COAT group, this is a COAT group, these are electron withdrawing group, withdrawing the electron towards itself, and this is again a nitrogen over here. So 3 electron withdrawing groups are attached with this carbon atom. Now this hydrogen becomes highly acidic. So being acidic, we are using a base. This hydrogen will go from here. Okay, having a this hydrogen will move from here as an H positive because base will give base will satisfy that hydrogen. That's why this hydrogen will leave this system like that, and having a carbon ion over here. And once you have a carbon ion here, we can enter a side chain, what we desire, what we need for the synthesis of the amino acid. We need here amine SCH2CH2. So the starting material for that is we have halosulfide. This is a halogen. Actually, alkyl halide are the very good nucleophiles. You can they can act as a they can act as a carbon chain producer. We can use them for malonic acid synthesis. So this is an alkyl halide. So this chlorine will move like that, okay, and this positive charge will go here. This becomes electrophile. Now this electrophile can easily attack over here, and this is converted into this one. So actually we are utilizing the virtue of malonic acid synthesis here, okay. Then now we want NH2 group here and carboxyl group. So what we will do, we will hydrolyze it. Once we hydrolyze it, this bond will be hydrolyzed because this is a amide bond. This will also hydrolyze and converting this moiety. This will hydrolyze. This will go. H will go here. OH will go here, and H will go here. OH will go here. This will convert it into this. So starting acidity. Phthalic anhydride, that is the phthalic and phthalimide. So this is the phthalic acid. This is converted into phthalic acid, and the remaining moiety is this one. Actually, we are doing alkaline hydrolysis. So initially, this will form here CO minus. Then this CO minus is protected by the proton. Then we are acidifying it to this is carboxylic acid group. Similar reaction will take place here. This ester will be hydrolyzed, this ester will be hydrolyzed, and we have geminal dicarboxyl group. COH here, COH here, and geminal dicarboxyl groups are highly unstable. They will undergo simultaneous decarboxylation. Now this is the decarboxylation process. This is the decarboxylation. COH is moving from here, and this H will go here, and we have this desired amino acid. This is next one. So by using this Gabriel salinide procedure, you can synthesize any amino acid just varying this side chain. Okay. Another procedure where we can use the carboxylic acids or its alpha haloderivative is the direct nitrosation. See, we have to introduce NH2 group whatever here for the alpha halo acid for the synthesis of amino acids, because when we hydrolyze it, this diester will convert into COH, and this dicarboxylic acid will undergo simultaneous decarboxylation. We have COH and CH group from here. So this group can give us simply by hydrolyzing it and decarboxylating it, COH-CH molecule. And our aim, we want a NH2 group here. So by introducing an NH2 group, we have done here. We are using this potassium phthalimide here. Now we are not using here potassium phthalimide. We are using nitrosation process. We will simply introduce nitrogen here by this nitrosation process using SNO2, which is prepared by HCl and NaNO2. This is in situ preparation of nitrous acid. When this nitrous acid is with this diethyl malonate, it will give this oxime type molecule. This is C-NO2. Now once this N is introduced here, it can easily convert into an NH2 group. So this is reduced by zinc acetic acid. So it will give NH here, and this is converted into, then further this NHOH, this will give NHOH, this C-O, N-C is reduced, and this is converted into NHOH. And this NHOH, because we have to do further reactions, and this NH2 group will be protected. We will protect this OH group here. Why we will protect this OH group here? Otherwise, this OH group may interfere with the further course of the reactions in this step. That's why we are protecting this OH group by extraction reaction. This OH group, this NHOH group, this is NHOH OH group is protected after reduction. We have NH-OH group over here, and this OH group is protected by acetylation, and this is converted into ester. Okay. By acetylation process, this OAC, that is actually OCOCH3 group. This COCH3 group is the acetyl group is coming from this acetyl anhydride molecule through acetylation reaction. Okay. Then the same procedure, same step. This is active active hydrogen. This is active hydrogen group. With this nitrogen base, we have a negative charge here, because proton will be extracted by this proton is extracted by the base. So this is a negative charge, and again this Rx. This is Rx. Is converted by. Why we have done CO? We have taken COT here because we need a COH group over here. That's why we have designed such a starting material here, such a reactant here. So this designing of the reactant, it depends on the structure of the amino acid what you want. Okay, so you must know the structure of the amino acid if you want to synthesize. So this chlorine will attack over here, and we have this one. Then we have hydrolyzed it. We will hydrolyze it under hydrolysis. This bond will be hydrolyzed as ester. This bond will be hydrolyzed, getting converted into an ester molecule. This is here is COH. This ester will be hydrolyzed. This ester will again hydrolyze, and this ester will hydrolyze. The COH, COH, and COH. This is geminal dicarboxylic acid, which will undergo simultaneous decarboxylation reaction, giving this NH2COH, and this is the chemic acid molecule. So this is another method from which by using carboxylic acid to synthesize the various amino acids, alpha amino acids.